Hi, my name is Michael Eiler. I'm a digital lab manager here in the Electrical and Computer Engineering Department at Brigham Young University. Today, we're going to be talking about basic passive components, how to use them, and why they're important to circuit design. First, we're going to start with switches. Switches come in a variety of packages. You got things like pole versus throw, momentary versus latching, so let's break it down and start with a very simple example to begin with. Single pole, single throw. So a single pole, single throw, you have one option and one input, or one selector. Super basic, basically it's either connected or it's disconnected. If we go on to just a slightly more complicated example, like the single pole double throw, we have two options to pick from and one output. So this would be a single pole double throw. You can kind of extrapolate this onto the other examples down below, like a double pole single throw has two outputs and only one option for each output. So that's a double pole single throw because those are connected with the same switch. Or we have a double pole double throw. So two outputs. Whoops, don't know what happened there. Let's erase those errors so it's less confusing. Two outputs, and each of those outputs has two options to select from. Again, that would be a double pole, double throw. All right, now let's talk about momentary versus latching. Momentary is pretty straightforward. Basically, it means that you have a switch that doesn't like to stay connected. So if you push it once and you let go, it's going to come right back and disconnect itself. You will typically see those with things like these breadboard switches right there, or this limit switch right there. Those are both momentary switches, which means as soon as the pressure is released, the connection breaks. Latching, on the other hand, like to stay in place. The rest of these examples, we got sliding switches right there, we got rocker switches right here, we got a latching push button, we got these two toggle switches, three toggle switches right there. All of those are latching, and also this dip switch down here. So that kind of like momentary, except for exactly the opposite, so I guess not anything like momentary. As soon as you release the pressure, the connection remains in place. And I think we've covered most of these types. So we got button, like we talked about before. That includes limit switches, sort of. Limit switches are defined by this nice little arm there, which makes it really easy to detect when you've reached them. It's sort of like a lever arm. So those are limit switches. Slide switches, it's really easy. They slide back and forth. Limit switches, we just talked about those. Rocker switches, they rock back and forth, so you'll often see those on like power switches or things like that. You would definitely not want those to be momentary. That would not be good for your computer. Rotary switches. We don't actually have any examples of rotary switches, but essentially those just have a lot of circular switches on the bottom and usually a wiper in the middle that as it spins around, it allows you to connect to the different outputs. And finally, the dip switch, this one down here, stands for dual inline package switch. And that basically has a bunch of single pole, single throw, typically, switches that you can toggle on or off in a nice compact package. Next, let's talk about resistors. Resistors are these amazing components that help us resist the flow of current. And that doesn't sound super useful. However, it can provide us numerous measurements or help us control things and help us regulate circuits. So let's get into some of the basics. So a symbol for a resistor in the US is just your typical squiggly line. And the European symbol is an empty box, usually about the same size. The value of the resistor would be listed usually directly next to it or inside it. The units for it are stated right here. They're ohms. And the impedance is itself. So let's talk a little bit about impedance really quickly. Just like a resistor resists the flow of current flowing through it, impedance is how much it resists a signal coming through it. And that's not a great line. Let me redo that. So essentially what that means is, and especially for this case, if you notice there's no frequency component, it's just the resistance. So it is directly proportional to the resistance of the resistor. So if I hadn't said resistance enough. Let's talk about different types. So most of the ones that we sell in the shop are these kind of slender bodies. I don't know what happened there. Let's try that one more time. All right. They'll usually have four or five colored stripes. And those stripes denote the value of the resistor. You can look it up online, or you could just use a multimeter. Those range in power from quarter watt up to 5 watt. And you can typically tell based on the size of the resistor. They're not obviously this big. They're usually much smaller. And you can also tell by the thickness of the lead. So generally speaking, the thicker the lead and the bigger the package, the more current it's capable of carrying. Speaking of carrying more power or more current, power resistors are another thing that we do carry in the shop. Those typically have a different use than your typical carbon resistor. And you could tell them apart because they are vastly different. Their entire body is essentially a large heat sink. So you'll see a bunch of kind of like a big metal finned package with some sort of mounting hole in the front. That is awful. Mounting hole in the back. And then the little connection. That's going to bug me, so I'm going to redraw that really quick. All right, let's just pretend that looks good. So there's your typical power resistor. Those range from 5 watts all the way up to 100 plus. You know, we have ceramic ones as well. They're just massive behemoths. So next, let's talk about variable resistors. These come in a variety of packages. Some of these, like potentiometers, trim pots, as they're sometimes called, or pots, or rheostats, all measure motion or movement. For instance, potentiometers and trim pots are both very similar. They act the same. They have a large spool of wire with a pin on each side, obviously, and then a single wiper coming out the side. So you'll typically see them in 3-pin packages. So it's pin 1, pin 2, and pin 3. They're just to be safe, check the data sheet. And just like wire has a natural resistance along its length, the longer it is, the higher the resistance. The further down this wiper goes or travels, the larger the resistance between 1 and 2. So for instance, the resistance between 1 and 3 will always be the same. Let's say this is a 10,000 ohm potentiometer or 10K ohm potentiometer. That will always be 10K between these 2 points. However, the resistance between 1 and 2, or R sub 1, 2, is directly proportional to how far away, or the distance between 1 and 2. Another cool fact for you is the resistance between 1 and 2 is equal to the resistance between 1 and 3 minus the resistance between 2 and 3. So the sum of those will always equal, so the sum of 1 and 2 and 2 and 3 will always equal 1 and 3. So anyway, cool fact for you. Let's see, photoresistors are pretty straightforward. They are essentially a resistor that changes its resistance based off of the amount of light that's hitting it. So it's great for measuring the amount of ambient light in a room, or if a light's shining on something, you could use it for that. Although you'd have to use some sort of shielding around it to make sure that it doesn't get kind of leakage from the sides. And thermistor, as it might denote, measures temperature. I'm not familiar with the symbol because I never really use these, but I would probably do something like that to denote that it's a temperature-based resistor. Let's talk about the uses next. So, like we said before, they resist the flow of current. This is pretty straightforward, although it may seem counterintuitive, or why, like you might wonder why that's useful. Let's use a simple example of a LED. So a typical LED, at least the ones that we carry, let's draw those little light things coming out, will look like, or a typical LED circuit will look like this. So we know that an LED usually, and again I'm kind of bouncing over the place, the ones we carry only like to operate at about 10 milliamps. So if you try and put more through that, you can, but at a certain point the LED will be very, very bright for a very short period of time and then will never work again because you burnt it out. So to limit the amount of current flowing through the circuit, we know that from Kirchhoff's current law, like we talked in the last video, the current flowing in or out of the battery into the LED is the same as the current flowing out of the LED into the resistor, which is the same as the current flowing out of the resistor and back into the battery. So we know that we can use this resistor to limit the flow of current through that LED. And to calculate that, we would use Kirchhoff's voltage law, or we would apply Kirchhoff's voltage law, which states that the sum of the voltages around a loop is equal to 0. So we have 0 equals voltage from this battery right here, VB, minus the voltage drop across the LED, which we'll talk about later, but let's just assume it's like 3 volts or something like that, minus the voltage drop across that resistor. So let's assume we have, let's keep it general, why not? So V sub R equals V sub B minus V LED. All right, now because of Ohm's law, we know that V sub R equals our current I times our resistor R. So if we wanted to select the proper resistor for that, we would say R equals V sub R over I, or V sub B minus V LED over I. So if we had a, let's say, a 6-volt battery and a 3-volt LED drop, let me label those so it's a little less confusing, and we wanted 10 milliamps flowing through our LED, we would plug that in. We would get 6 volts minus 3 volts divided by 0.01 amps, which gives us a value of 300 ohms for our resistor R. All right, so that's how you use a resistor to limit the flow of current through something. Part of this is not only limiting the or controlling the current, but also using that to determine a voltage drop. Let's talk about this, and I'm not doing a great job of explaining it, but I promise it'll make more sense in just a little bit. Let's talk about voltage dividers. So for instance, if we wanted to measure the voltage drop here, right, because of Ohm's law, we know it's going to drop a certain amount, and we assume, and this is very important, that there's no current flowing out here at our V out. So if there's no current flowing out, that means that all the current flowing through here flows across these two resistors. We'll call R1 and R2. This means that we can determine the exact value of V out without even having to worry about the current flow. And let's talk about that really quick. So we know from Ohm's law that V in minus V out over R1 equals I, the current flow, which we know is also equal to V out minus 0 volts or ground over R2. Now we can simplify this and say that R2 times V in minus V out is equal to R1 times V out. I'm just going to leave off that 0 volts there because that's 0. Hopefully that's obvious. And let's simplify this a little further. So we have V in times R2 equals R1 times V out. Or let me simplify that a little more, if you'll forgive me. V out times R1 plus R2 from the other side of the equations, because it's negative when you flip it over, it's positive. This is further simplified by saying V in equals V out times R1 plus R2 over R2, which typically we want to measure V out and not use it to calculate V in. We would say that V out equals R2 over R1, R1 plus R2 times V in. All right, now this equation is for voltage dividers. And if you notice, again, the current, because there's no current flowing out, is not in the equation, right? We don't care what the current flow is. All we care about is the amount of voltage at the input and the values of our resistors, R1 and R2. Okay, now, we talked about voltage dividers. This is great. Like if you wanted to measure the battery voltage of something, that's wonderful. Please don't use this for a power regulation, right? To drop the voltage for a motor or microcontroller. And let's talk about why really, really fast. If you remember from our last slide or our last lecture, power the power law is P equals I times V. So in this case, we have, and if we want to simplify using Ohm's law, we know that power equals V squared over R. All right, so any voltage that we want to drop over resistor 1 is going to be equal to this. Or I guess any power we drop over the entire thing is going to be equal to that. And that gets really big really fast. It's not efficient. Plus, if you were to hook up something to this, you would have current flowing out at V out, and that changes the entire equation. So voltage dividers are great for measuring things, but not for powering things. Just keep that in mind. All right, I think we've done enough damage on this. We'll come back to applying voltage dividers in just a second, but keep in mind, like I said, you could use this so if Vn was variable, like if it was a battery voltage, and you wanted to measure that battery voltage, but you can't actually measure a voltage that high. So like if you wanted to measure a 9-volt battery with an Arduino, it can only measure 5 volts. You would have to use a voltage divider to drop that voltage down evenly. So it's not going to change, or like it's a linear relationship, right? Because R2 over R1 plus R2 is linear. And then we would be able to use that to drop 9 volts down into something that you can measure with a 5-volt analog input. All right, sorry, that was a little confusing. Like I said, we'll get back to using voltage dividers and applying them in variable situations. But another really quickly useful thing that resistors are useful for is a pull up or pull down resistor. And let's talk about that for a second. So if we have a little microcontroller here, and we want to have a input that says, hey, if we close this switch, that means something. So maybe you have a button that turns on an LED on the other side. Yep. With some code. And yes, I know that's not the most efficient way. It's a little contrived, but you'll see why this is important in a second. So with this 5 volts here, right, if the button is closed, then that connection is made, and all of a sudden this reads 5 volts at this line. So if closed, then we'll call this Vin or VM for V microcontroller or V micro. All right, if closed, then V micro equals 5 volts. But what if it's open? If it's open, then V micro isn't attached to anything. It's called floating because there's no defined voltage for it, right? Remember, voltage is potential energy. It's all related to something. So if voltage is floating, it's kind of like having a ball with a mass m. Oh, let me draw that a little more clearly. But no ground, right? It's really hard to calculate the potential energy of an object, which potential energy equals mgh, without the h, right? That h requires there to be some reference for us to understand where our ball is, how high off the ground it is. So, all right, in order to provide that reference, we need to use a pull up or a pull down resistor. Now, if we used a pull up resistor, that wouldn't help because it'd be connected to 5 volts when the switch is open, and it'd be connected when the switch is closed. So that doesn't really help. So in this case, we would use what's called a pull down resistor. And basically what that means is if that switch is open, instead of it being an unknown value, we know that it's going to be 0 volts because it's tied to that ground. Now, you don't want to use a very small resistor because of our power drop, right? We want to use something that is a large enough resistance that it resists the flow of current going through there, right? We want that to be minimal current flow. And we want this to be minimal current flow as well. So essentially, we're only using it as sort of a voltage reference. Typically, for pull up or pull down resistors, you use a 10 kilo ohm. Let me write that a little clearer. A 10 kilo ohm resistor. That works great. It's large enough that there's a very low power drop, right? If we calculate this really quick, P equals V squared over R. And that gives us 25 divided by 10,000. Which is really, really small. small. I don't want to calculate that. It's not too hard. I just don't want to get around to it. However, if it's too large, because you might be like, great, let's just throw a massive resistor on it. We'll talk about this maybe more later, but it essentially, there is some capacitance associated with that, and it would take a long time for it to drain. So 10 kiloohms is a great value to use. One more thing that we need to cover is how this actually works without kind of breaking the laws of physics. So pull up and pull down resistors are essentially a voltage divider. If we look at it like this, right, we have 5 volts with a switch, and then we have our V out going to the microcontroller. And then we have a resistor down here. So if this is R1 and this is R2, we can quickly write this equation as V out equals R2 over R1 plus R2 times 5 volts. And you might be thinking, well, that's not a resistor, it's a switch. And you're like, yes, that's true, but a switch, when it's open, has a very large resistance due to the air gap. And when it's closed, it has a pretty small resistance. So we can look at it that way. So if it's closed, so I'm going to write if closed again, right? Then we essentially have R2, which is something very large. We'll say 10,000 ohms or 10 kiloohms over something very small. We'll say it's 0 plus 10 kiloohms. So if it's closed times 5 volts, we get essentially 5 volts. Finally, if it's open, we get something large like 10 kiloohms over something very large. We're just going to call it infinity for simplicity's sake, equals, surprise, surprise, 0 volts. So I promise the math works out. This is an example of a pull down resistor. The pull up resistor, you simply switch your values and the thing works again. So the only reason you would use a pull up versus a pull down is in your code if you wanted to have something kind of is more intuitive, like if you had we'll get into more applicable situations later, but both are useful. Really, it's just case dependent. Okay, let's move on to measuring current or heat or light or position or anything like that. And current is kind of different. You do use a resistor for this. It's typically a very small resistor, like a 0.1 ohm or a 1 ohm, and it's very high wattage, so it's a power resistor. This is also called a shunt resistor. Essentially, that voltage drop allows us to calculate how much current is flowing through it without wasting too much power. All right, now that we have that out of the way, let's talk about measuring heat or light or position. So the simplest one I like to talk about is measuring position or light. We're going to go back to that voltage divider equation. So that's ground. That's great. And we have our V in, R1, R2, and V out. So let's start with measuring light. Okay, so if this is a photoresistor, if it's light, then the resistance will be very, very small. So we could say that V out, we remember this from last time, equals R2. I should write this up here. V out equals R2 over R1 plus R2 times V in. So if it's light, we have a very small resistance, we'll say 0, over R1, whatever that is, plus 0 times Vn. And let's assume that this is a 10 kilo ohm, because that's a good value to use. It's almost like a pull-up resistor. Ooh. All right, so we'll just replace that 10K right there, and we get 0 volts. Now, if it's dark, we have a very large resistance. So V out equals, we'll just say infinity over 10K, whoops, 10 kilo ohms plus infinity times Vn. And no, you don't have to use L'Hopital's rule because we're just going to assume that this is equal to Vn. All right, so you can see how we now know that, because voltage is very easy for us to be able to calculate, right? We know that if we have 0 volts at our V out, if we were to measure that with like a microcontroller right here, if we had 0 volts there, we would know that the light is on, and if we had a voltage there equal to whatever Vn is, then we would know that it was dark. And obviously we could flip these two, right? If we put the photoresistor up top and the R1 down here, then the logic here would switch. I'll leave you to derive that if you really want to. The same is true for measuring position. So if this guy is a potentiometer, instead of pulling it here, we would actually connect this to the wiper. And what that does is, and hold on a second, I gotta think about this. Yes, I think that works. Okay. We'll do this instead. All right, so that's going to still be connected to the junction. This guy, however, is going to be connected to ground. So this guy will be floating. You could tie him on there. If you did that, this would kind of act more as a rheostat. But we're just going to leave him off for simplicity's sake. All right, so now R2 is equal to whatever that value of the potentiometer is. So if it's all the way at the top, we would have V out, right? So if it's R2 is small, so we'll say is close to 0, then if V out would equal Vn times something very small over 10 kiloohms times, or plus 0, and that gives us 0 volts. However, if R2 is very large, then V out would equal Vn times, let's say it's a 10k ohm pot, 10k over 10k plus 10k, and that would give us 1/2 of Vn. So you can see it's not giving us all of Vn, but that still gives us a decent range. So in this case, we would probably lower the value of whatever Vn is. We don't want to go too small because remember all of that voltage drop is still going to have to go through here. But we could fluctuate the value of R1, or we could choose a specific R1 to meet our needs. So anyway, getting back to business, this is how we would use a voltage divider with a variable resistor, whether it's a potentiometer or whether it's a photoresistor or a thermistor, to measure certain things. Power loads. So let's say you're designing an amplifier and you don't want to blow up your really expensive speakers, or you want to test a motor driver and see if it can really handle all of the power that your motor is going to draw. Without burning out the motor or your speaker set, you would want to simulate it with a power resistor. And that's essentially what using resistors for power load is. Let's move on to useful equations. So resistors in series would look something, oh man, I don't know why it does that sometimes. Resistors in series look like this. So we have R1, R2, ... Rn. All right. Remember how we talked about how wire has a natural resistance over its length? You could think about this like a giant resistor, R total, which is equal to the sum of all its individual parts, R1 plus R2 plus ... plus R sub n. All right, pretty straightforward, nothing to worry about too much. It's just the sum of the resistors. Now resistance in parallel is a little trickier, but let's sketch this out. So that would look something like the following. If we have R1 and R2 and R sub n, this is equal to R total, and I'm actually going to start with R total over 1, is equal to 1 over R1 plus 1 over R2 plus ... plus 1 over R sub n. What this works out to be is R total equals the sum, the product, R1 times R2 times R ... times Rn over R1 plus R2 plus ... plus Rn. All right. So this is the equation for resistors in parallel. A little trickier, but there you go. Let's get into capacitors. So a symbol for a capacitor is pretty straightforward, and it kind of represents what's going on under the covers. So we have all of these electrons stored up on this side, and it kind of pushes away the electrons on the other side, so we get a bunch of holes. And this leaves us with a net voltage storage, kind of. Another way to think about this is if you have a pipe that's connected to a pipe next to it, and you had a kind of a rubber membrane right there, voltage, remember, it's potential energy or pressure in terms of fluid, and so it can kind of push down on this or push out. And so this motion of that diaphragm of sorts acts like our capacitor and stores voltage. All right, so the symbol for it, let's see. So we got this one where it's just two plates. We also have this one where it's a plate and a kind of curly part. And sometimes they'll add a positive indication on there. So this would be for a polarized capacitor, that bottom one. The other two would be non-polarized. Units are in farads. Typically, you don't see a whole farad capacitor. The most common ones are microfarads. Whoa, that's a messy micro there. Let's see, 1 microfarad. Or you might see, like, so anywhere between, let me look at my notes just so I don't get this wrong. Anywhere, I mean, you'll see picofarads, right? Picofarads, you'll see nanofarads, you'll see microfarads, you'll see millifarads sometimes, although those are really rare. And then you'll typically just see farads. But those are for really big power applications. So most common, or at least most of what I see, are these three right there. And let's talk finally about, let's talk about reading them as well. So if you see something like a 104 capacitor, what that means is 10 with 4 zeros after it, so 100,000 picofarads, which is a very useful measurement. If we were to write this out, it'd be 10e to the, or whoops, 1 e to the 5th. Picofarads are e to the minus 12. So that leaves us with 1 e to the minus 7, which is the same as 0.1 e to the minus 6, or in other words, 0.1 microfarads. So kind of long, laborious, but you get the picture. All right, let's talk about impedance. So impedance, or the, like I like to put it, the resistance towards frequency. Remember, for a resistor, Z sub R was just R. Now in this case, we're looking at capacitors, not resistors. So Z sub C, like it says here, is 1 over J omega C. Yeah, J can be on, well, yeah. Anyway, 1 over J omega C. And what this gives us is omega, or the radians of our frequency. So to convert to hertz, you just multiply or divide it by 2 pi, or frequency you would multiply by 2 pi to get omega. So if omega is large, so if we have like a, we'll just simplify it. If it's infinity, the impedance of this is 1 over J infinity times C, or 0. Now, if the impedance is, or if the frequency is 0, we get J times 0 times our capacitance, C. That is infinite impedance. So capacitors like higher frequencies than lower frequencies, or they let more signal pass through. All right, let's talk about the different types. So mica are kind of uncommon, at least nowadays. They sort of look like a molar. I feel like a very decayed brown molar. But they always have those double humps like that, and they're a dark color. They are non-polarized. That's important. So it doesn't matter which way you plug them in. They're typically used for things like radio, which is why we don't use them a lot anymore, sad to say. But they have a very high frequency capability. They're very good at high frequencies. And kind of a lower voltage, 50 to 500 volts is pretty typical. All right, the one that you will see almost all the time are ceramic capacitors. So those are usually some sort of ball or disc or square, right? Doesn't matter. They're very thin. These ones are kind of bulgy. These ones are very disc-shaped. Sometimes they have a little bit of bulge to them, but the way to tell them apart from the others is they are not polarized. So there's no indication of polarity on these. They are very good at high frequency. They're very cheap, and they're very, very high voltage. You can see it's up to like a kilovolt. It's totally fine. Or yeah, it's just great. So those, and then they'll usually have the number like 105 would be a 1 microfarad capacitor. Now tantalum can easily be confused. I think, and I've been told, they kind of look like balloons. I agree with it. They're lots of different colors. The way to tell them apart, besides they are much more glossy, so they kind of have a little shine to them. Let's see if I can put that on there. Is they always have a positive rail indicated. So they are polarized, and it's the positive side that's denoted. And you can see it's very low voltage. These are really good at medium frequencies. They're better than ceramics and better than electrolytics. So they kind of fit that niche. Finally, electrolytics. So these are for very large capacitance. These almost always you'll see them in what kind of looks like a big tin can. They got a big metal cap on the top, and they'll have they're usually a dark color like black or blue, and then they'll have, let's see if I can draw that, they'll have a negative terminal indicated on one side, and the positive terminal is on the other side, or is not indicated but is the other side. So electrolytic and tantalum are both polarized. Mica and ceramic are not polarized. So hopefully that makes sense. If it doesn't, feel free to stop by. Okay, let's talk about some of their uses. So like we mentioned earlier about the two pipes, capacitors act as sort of a buffer or a diaphragm to absorb a voltage and to store it. So they absorb voltage spikes and they store voltage. This is particularly useful if you have a voltage spike, if you have noise, or if you have something that you want to kind of filter out. So let's talk about filtering for a bit. So hopefully you remember when we talked about voltage dividers, where we have R2, R1, V in, and V out. And just as a quick refresher, V out equals R2 over R1 plus R2 times V in. Now this is great for voltages, right? Because if you remember, as current passes through here and not through there, don't forget, it causes that voltage to drop, giving us this nice, neat little voltage divider. Now what if instead of looking at current, we wanted to look at impedance? So I'm going to erase some of this stuff and redo this with a capacitor on top and a resistor on the bottom. So one easy way I like to think about high pass is the capacitors on top. It's not why it's a high pass, but we'll get into that in a second. So we have our capacitor C and our resistor R, and let's write their impedance. So Z sub C and Z sub R. And remember, the impedance of capacitor is 1 over J omega C. And for a resistor, it is just R. All right, now we have our equation Z sub R over Z sub C plus Z sub R. And that equals R over 1 over J omega C plus R times Vn. Now if we multiply the top and bottom by J omega C, something magical happens, and we get R times J omega C over, oops, that's a C, 1 plus R times J omega C times Vn. All right. And this is equal to V out. I'll just make sure I did that right. Yep, that all looks good. So if, all right, here's our equation for a high pass filter. If omega is very, very large, say infinity. Huh, weird. Keep running into that. All right, so if omega is very large, we have 1 over, or infinity over 1 plus infinity times Vn, which, for you non-math folks out there, is just 1 times Vn means V out equals Vn. So this is little to no attenuation. This is why it's a high pass filter. So high frequencies, if we were to look at a Bode plot, high frequencies are able to pass through just fine, but lower frequencies are attenuated, or they become less impactful, they're less noticeable, they're filtered out. And this cutoff right here, F sub C, or our corner frequency, is equal to it's equal to omega divided by 2 pi. Yeah, well, that's how to relate it. Anyway, okay, so let's talk about low pass filters. So low pass, we're going to switch positions where the capacitor, hold on. The capacitor is underneath and the resistor is on top. So we have V out, we have C, we have R, we have V in. The impedance Z sub R equals R, and the Z sub C equals 1 over J omega C. And V out equals, in this time, it's Z sub C over Z sub R plus Z sub C times V in. Let's fill those in. We get 1 over J omega C over R plus 1 over J omega C times V in. Now we're still going to multiply the top and bottom by J omega C, and we're left with 1 over R times J omega C plus 1 times Vn. Okay, now that's V out. Okay, there's our equation for a low-pass filter. So if omega is large, we get 1 over infinity plus 1 times Vn, or in other words, 0 times Vn, or just 0. So V out equals 0. So ultimate attenuation. However, if omega is very small, like 0, V out equals, let's see, 1 over 0 plus 1 times Vn, or in other words, Vn. So little to no attenuation. So this is why it's a low-pass filter. So again, let's draw that Bode plot. So low frequencies are unattenuated, higher frequencies are attenuated, and right there's our cutoff frequency, which we can find by using this equation. Omega equals 2 pi f. So there we go. And I guess that's probably a better way to talk about this. So a little correction there. F equals omega over 2 pi. There are equations to find the cutoff frequency. You can talk to us about that later. All right, so removing noise. Now, if you think about it, noise is a high frequency signal. So if we have our circuit, very useful here, and we have our microcontroller here, and this is a noisy signal. There's a lot of noise on it. The easy way to get rid of this is you put what's called a filtering capacitor right there. So essentially what's happening is we assume that there's some inert resistance in here, right? I guess I should draw it. So there's some resistance in that circuit, or even just in the wire itself. And when you compare that with this capacitor here, we essentially have and this is a noise. In this case, this is actually our low pass filter. So the lower frequencies, the signals we're trying to measure, are able to pass through, while the higher frequencies, so not the resistor, sorry, that's R, that's a resistor, that's a capacitor. The noise right there is filtered out in our low pass filter. What about decoupling? So a DC signal is actually a infinite frequency, which sounds weird, but essentially the same thing as last time. If we have, and let's describe it like this. So if you have some signal up here, and let's say you want to measure it down here, right? Same signal, you just want to get rid of this, what's called the DC offset. So to get rid of that, you can use a decoupling capacitor, and it's as simple as this. So if we have our circuit, whoops, right there, and we have our noisy signal, or not our noisy signal, we have our high frequency, or our DC offset signal. If you just put it through a capacitor, the output is just like that. There's no DC anymore. We've completely stripped it off with that capacitor, because remember, it allows lower frequencies to pass but kills high frequencies such as DC. All right, now let's talk about some useful equations with capacitance. So capacitors in series would look like this. And the equation is a little ugly. So C total equals 1 over C1, C2, C sub n, plus 1 over C2, plus dot dot dot, plus 1 over C sub n. And what it comes out to is C total, whoops, not tattle, C total equals C1 times C2 times C dot 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 times C sub n over C1 plus C2 plus dot 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 plus Cn. All right, there is capacitance in series. Kind of gross, but that's the truth. Now for capacitance in parallel, the nice thing about this is, remember how we talked about those two plates? We essentially have those two plates are just now giant plates. So we have C1, C2, C sub n. So C total in this case equals C1 plus C2 plus ... plus C sub n. Great. This is really nice if, let's say, you wanted to have an odd capacitance value, or if you wanted to filter out things at different frequencies, you could combine electrolytic and tantalum and ceramic capacitors if you really wanted to use tantalum. But you could combine capacitors of different materials to get a better capacitance at a larger range of frequencies. And that's all we have for capacitors, so we'll move on to inductors now. Unless, let me check my notes really quick, but I think that's it. One other useful thing for capacitors. Let's go all the way back. So in storing voltage, that's really useful in, like, if you had a power supply, right? So if we have this battery here, with our negative and our positive lead, and we draw this off into our circuit, there's going to be some noise there. So if we just add a little capacitor there, just like we talked about with a removing noise, or a low pass filter, this essentially will smooth out that signal coming off of that power supply. Alrighty, let's see. I believe that's it. Okay, yeah, let's move on to capacitors. Okay, so capacitors, their symbol looks just like their part. It's basically a lot of wire in a loop. Their measurements are in henries, although typically you'll never see a 1 Henry inductor. That'd be a really big inductor. And their impedance, in this case, instead of it being under, is over. So again, impedance, remember, is the resistance towards frequency. So there's our omega component, or there's our frequency component, omega. So let's talk about types. There are two main types. So there are air coil inductors like this guy, and then there are iron core. And what that basically looks like is it's just a standard inductor, but it has this big core in the middle of it. That iron core actually helps to increase the inductance without needing to use more wire. So some uses of inductors, they store current. So unlike capacitors, which store voltage, inductors store actual current. So kind of a good analogy is if we have a water wheel here with water flowing out, right, as it, let me move this a little bit. With water flowing out, right, there is water stored in these before it can kind of flow back out into our pond here. So that storage, that stored fluid or stored current for inductors, helps us to kind of preserve momentum as we're moving through things. So this is really useful in electromagnets, specifically in motors and solenoids. But magnets and solenoids are very closely related. Solenoids are basically a hollow electromagnet, but they have a core that can move. So we'll talk more about motors later, but briefly, let's go over those a little bit. So types of motors, you have just your standard cheapo DC motor. So just like that. So they're brushed. They don't care which side is positive and negative, meaning they're unpolar or nonpolar. A little upgrade from that, you have, let's see, you got brushed or brush. This is a brushless or brushed. Brushless are a little fancier. They use inductance to actually drive that motor. So instead of brushes changing the polarity of this magnetic coil, it uses inductance natural in the coil itself, which is kind of cool. You also have stepper motors, which have the coils on the outside. And the fancy thing about that is it means that if you have a single coil or a single permanent magnet inside, or a series of permanent magnets, you can get a high degree of resolution in there. Often like 220 steps, they're called, or spots per revolution. So very, very good. Then you have servos. These have higher resolution than steppers. And they also, like, we're talking like tenths of a degree. It's really nice, a 0.1 degree. Then They're typically limited between 0 and 180 degrees of motion, though, unless you get continuous. And continuous, basically, they pretend that they're always at 90 degrees, and so if you tell it to go to 180, it's going to go really, really quick this way. And if you tell it to go to 0, it's going to go really, really fast that way. And then to get it to stop, you just say, hey, you're at 90, congratulations. I think that's pretty much it, or at least that's all I'm going to go over. There are lots of other types of motors. These are kind of the important ones. So one thing of caution that I should bring up with, when you're using inductors, they create what's called an inductive spike. So if we were to look at voltage, it's this large spike in voltage as you turn it on and turn it off. So you often have to include things to prevent that. We'll talk about more about how to mitigate inductive spikes later, but just keep in mind that is something you need to watch out for. Transformers. Transformers are super, super cool. What they allow us to do is they allow us to increase the amount of the amount of voltage or the amount of current in a circuit. And the way they work is basically you have one coil, and then you share a metal loop, and then you have a secondary coil which has many more turns. So and this is our secondary coil, and this is our primary coil. And let's say that our secondary coil, let's say it has twice as many loops as our primary coil. All right, so the voltage at the secondary, and here, let me write it here. So if we have some voltage at the primary, and keep in mind, with Lorenz's law, so with electromagnets, that magnetic load, or that magnetic pulse, I guess, let me rephrase. With transformers, it only works if the frequency, or if there is some alternating current. As soon as the current is steady, the transformer stops working. So we have our voltage at the secondary, our voltage at the primary, and our current at the secondary, I sub S, and our current at the primary, I sub P. So voltage at our secondary equals the voltage at the primary, whoops, don't know what happened there, voltage at the primary, times the number of turns on the secondary divided by the number of turns on the primary. And current is the opposite, so it equals the current at the primary times the number of turns of the primary divided by the number of turns on the secondary. So very, very useful. This is only useful, though, if you're working with alternating current, or AC voltage. All right. You can use them for filtering. I'm not going to go into it. However, it is a more powerful filter. So with RC filters, they're called, you kind of get this slower roll-off because they're a single pole. And you can learn more about that later. But these are what's called a secondary pole. So probably not that sharp, but they're still much sharper. So this is because it has two poles. Again, go ask your professors if you want more or more information, or you can ask Joe or I. So let's talk about some useful equations. So inductors in series would look like this. Oh crap, I'm just going to leave that little spiky there. Sorry guys. All right, where we have L sub 1, L sub 2, L sub n, and the sum of these, or L total is equal to the sum, which is very nice. I like that. And that kind of makes sense, right? It's basically one giant coil in that case. However, in parallel, which would look like this, where we have L1, L2, L sub n, just like resistors, L total, or 1 over L total equals 1 over L1 plus 1 over L2 plus plus, I'm going to take advantage of that, 1 over L sub n. Therefore, L sub total equals L1 times L2 times times Ln over L1 plus L sub 2 plus plus L sub n. All right. And finally, let's talk about inductance of an air coil. So this is kind of useful because oftentimes inductors are so particular for lack of a better term, you would typically buy them for a specific project. So in the ELC at least, we don't stock a very large variety of inductors, which is why if you're ever designing something that includes an inductor or a capacitor or a resistor or all three, right? So if we have like an RCL filter, which does exist, choose your inductor first because it has the least variety, it's the most expensive, and it's the least accurate. So if we want to talk about this, I'm going to go like this. So pick this one first, pick your capacitor second, and pick your resistor third, because cost goes up this way and accuracy goes up this way. So it's far easier to pick an inductor and be like, wow, this is, 20% of what it said it was going to be. The capacitor is going to be like 10%, and the resistor is going to be like 1 to 5%. So choose your inductor first, your capacitor second, and your resistor third. But let's talk about how to build a custom inductor. So the inductance of an air coil, so no core in there, L, equals D squared times N squared over 18D plus 40L. And I know that's really gross. I'm sorry. It's because it's in inches. Don't blame me. So D is the coil diameter in inches. In inches. Oops. Inches. And this is from the wire center to wire center. So remember, each of these wires has a thickness to it. So it's from the center of that wire to the center of that wire. So that's D right there. All right. N is very simple. It's just the number of turns. Number of turns. So in this case, we have 1, 2, 3, 4, 5. So 5 turns. Erase the 5 there. Sorry. Make it more abstract. And L is the distance between the legs, also in inches. Distance between legs. And what that boils down to is kind of how spread out the inductor is. So the more spread out apart, or the more spread out it is, the less the inductance, which makes sense, right? You want that coil to be tight if you want a higher inductance. That wraps it up for passive components. So we've talked about resistors, we've talked about capacitors, we've talked about inductors, we've talked about voltage dividers, we've talked about filters, high pass and low pass. We've talked about all kinds of stuff. Hopefully a lot of this made sense. If it didn't, like I said, you're always welcome to come to the ELC and ask us. We'd love to talk to you more about it. But until next time, when we talk about passive or active components, part 1, I'll see you around. Thanks so much.